Thank you so much. It's my pleasure to be here. So congratulations to the prize winner. And I'm so happy to see so many faces of colleagues that I haven't seen for a while. So it's a great opportunity. So what I'm going to talk about now are the massive stars. The stars that Connie apparently seems to love. I didn't know, Connie, that you love those stars so much. But I'm really glad that you do. So to me, massive stars are stars that are born with masses more than 8 solar masses, and what sets this mass is not the number so much, it's the end fate. It has to be massive enough to complete the entire set of evolutionary cycles down to the collapse, the core collapse, into a neutron star or into a black hole. So those stars are stars of the extremes. They are the most massive, the most luminous, the hottest, the bluest, with the most strong stellar winds, with the highest level of ionizing radiations. And it's not only the stars when they're born, but also throughout their evolution. So where am I here? So our sun is here in the middle of this temperature luminosity diagram, and the stars that I'm going to talk about are occupying the left, so the hot, and up corner, so the hot and luminous corner. That is when those stars are born, but when they evolve, as we've seen for the sun, the star is getting bigger by about a factor 100. For those stars, it's the same. They will try to get bigger by about a factor 100 and then become red supergiants, so move to the right-hand top corner of this diagram, and that's an important factor. There's a few other evolutionary phases, luminous blue variable, dwarf variable, but I'm just removing all of that at the moment because I want to keep things a little simple. Because, as Connie mentioned, there's been so many generations of those massive stars in the lifetime of the universe, they've had time to inject energy, chemical elements, ionizing radiation, and so on into the interstellar medium and even into the intergalactic medium. And the physics of those massive stars are really important ingredients in the models of many aspects of our universe, whether it is the evolution of galaxies, the formation of galaxies, the reionization stages of the early moment of the universe, the formation of the first stars. All of that depends on the physics that is coming from massive stars, so we call them real cosmic engines. And the stars that I'm going to study are much closer to us. We're not talking about the first stars and the distant universe, but I'm trying to bring to you some of the important elements in their evolution. So if the star is single, as I've briefly mentioned, the star will form from a giant molecular cloud. It will not form alone, but it will form as part of a cluster or an association. And in the single star evolutionary models, those stars are far away, so that the fact that they are in a cluster or in associations with many, many colleagues is not so important. The formation process itself, it's not understood. So I think I can put it plainly. But what we do know is that they will spend most of their life in the mid-sequence phase, burning hydrogen as hot blue objects, very luminous, and then they will evolve, they will grow as they are getting rid of their hydrogen, starting to burn helium. At the end of their life, so they will become a red supergiants, and at the end of their life, they will have a core collapse. There will not be any nuclear reaction in their core. The core will collapse under its own gravity. For the lowest mass of those massive stars, we think that this is accompanied with a supernova explosion that can be hydrogen-rich or hydrogen poor, leaving behind neutron stars. For the most massive of them, we think that they will collapse and form a black hole. What we don't know is whether there will be a supernova associated with it or not, or whether it's going to be a weak supernova. There's a lot of theories and a lot of ideas about that. The important physical ingredients in the evolution is, of course, the initial mass, but the internal structure, the internal rotation, as I'm sure George will mention in his talk in a few minutes, but also things like stellar winds, of course, metallicity, and I didn't mention magnetic field, because some of those do have a large-scale magnetic field, the origin of which maybe I can give you some of the elements at the end of this talk. Now, what happens if there's not only one star, but there are two stars that are close to one another? Well, formation, again, we don't understand, but let's assume that we have two stars. They are close enough. They're actually in a binary, so they are rotating around one another. But the separation of the binary is smaller than the size of a red supergiant. So when the primary stars will try to become a red supergiant, there's just not enough room in that system. And the outer layer of the primary stars will leave the zone of gravitational influence of the primary and will be captured by the secondary star. That's one example, one scenario, but what happens is that you transfer mass, but you also transfer angular momentum. And you were talking about rotation before, but this is the fastest possible rotation you can think about, because this is critical rotation. You cannot put any more angular momentum on the star. There's just, otherwise, the outer layer just evaporates. The star will continue to evolve. The primary will eventually explode, a supernova in this example, and then if the binary survive this, there can be other phases of mass transfer. The secondary will also try to get bigger, and maybe will transfer back mass on the neutron star or the black hole, forming what we would have seen most likely as a high mass X-ray binary. And in a small minority of the cases, you may, at the end of the life, form two neutron stars or two black holes that will be close enough that over time, through the emission of gravitational wave, they will get closer, 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 and then they will eventually merge, forming a gravitational wave events that we can now detect with our large-scale interferometers. So the important aspect of that, aside from any other ingredients in single-star evolution, would be the multiplicity status, whether it's in binary or not, the orbital separation, because that will tell you whether they will interact. They will also tell you when in their life they will interact. And the mass ratio, the difference in masses between the two stars, will tell you what kind of outcome you will have. Okay, so now there's a question, what is the most important? Is it single-star evolution? Is it the binary evolution? Well, what you would like to know is how many of those are in binaries that are close enough so that they can interact. So this is a diagram that we have seen before. On the right, on the horizontal axis, you have the initial mass of the primary. On the vertical axis, you have the multiplicity fraction. There are different versions of the diagram that have been published. That's a version that have been assembled by my PhD students, or former PhD student, Emma Baudier. It shows, it takes a lot of data from the literature. It shows that for the most massive stars, so around 10 solar masses and above, almost all of them are in binaries. That doesn't tell you yet whether they will interact. They will just tell you that they're in binaries. And we were wondering what is the origin of that binarity. And well, for that, we looked at the Messier 17, which is the Omega Nebula. It's a massive star-forming region that is probably less than a million years old. And we tried to look at as many massive stars as possible. And what we found is that every single of them is actually in a binary system. So this is telling us that the origin of the binarity of massive stars is deeply rooted in the star formation process. There are other clues. There is this system, which is observed by ALMA. It is 10 plus 8 solar mass object on a quite long period binary. They will not interact. But the eccentricity is quite small, which is telling you that this has not been formed by capture. So not only the lifetime is very short, but the eccentricity is so small that really it has to come from an in situ process. So those are elements that are telling us that the origin of the multiplicity, even if we do not fundamentally understand it, is coming from the star formation process. Now do I still have the sound? Okay, yeah. So I've been telling you there's a lot of binaries. What we would like to know is how many of those are close enough. And so that's part of the work that I've been doing with my team. We've been looking at different regions in the galaxy, in the Large Hadron Collider, so different metallicities, different cluster sizes, open clusters, associations, whether we look at the low mass massive stars, which are the B stars, or the high mass massive stars, which we call the O stars, we always find the same distribution, or close enough. We have a power law that goes from the smallest period of 1 day to periods of tens of years. Right. We do understand how you can form the wide one, but we cannot form the short period one. So one of the ideas that we have is that there seems to have a universal process, because you always end up with the same distributions, that maybe is hardening the binaries from the wide separation down to the lowest separation. And if that process is universal, tied to the formation process, maybe in a three-body dynamic or interaction with the remnant gas, then that would explain the fact that you always end up with a very similar distribution. So even if we don't fully understand where it's coming from, we do have that, and it seems that this is quite robust. There's hundreds of systems in this cumulative period distribution. Well, so there will be different channels of binary evolution. The very short period binaries, they will actually get in contact very quickly within millions of years, and they will form very peculiar kind of stars because they are so close to one another that the surface will touch and they will have the shape of a peanut. Those are interesting objects for the transfer of energy in between the two objects, because the surface properties are telling us that even if they are different masses, they have the same temperature, which is telling us that there's an energy transfer from the most massive stars into the atmosphere, into the atmosphere, within the atmosphere, but not to the surface of the less massive stars. The one that have period between a few days and a week or 10 days, they will most likely do stable mass transfer, and the more distant one will go to a very violent phase of interaction that we call common envelope. And this is just the first interaction. Even in this first interaction, you have different channels. But the truth is that if we continue thinking about it, there's so many different phases of interaction that we can more or less compute. Most of this is computing using one-dimensional models, right? So it requires a lot of mathematical tricks to be able to represent all those three-dimensional phenomena into one-dimensional models. So now I'm an observer. I would like to know whether this actually is a real story or whether this is just ideas that we've put and that seems logical, but nature is doing something different. So I would like to observe every of those different phases. And in green, I am highlighting the phases that we do observe, for which we have good statistics. We do observe a lot of young binaries. We do observe a lot of supernova explosion. We do observe, not so many, but we do observe high-mass X-ray binaries. We have 100 of them. Gravitational wave mergers, we now have more than 100 detections, so this is good. And then there's a few things that we have a couple of examples, but not so many. A few stars which we think are currently transferring mass. Double neutron stars or double compact object, we have also a handful of those. But then there are phases that seems to be important, like immediately after the interaction or immediately after the formation of the first black holes. Those we have not observed so far. And those are linked actually to some of the most uncertain moments in our model. Uncertain computation is the physics of the physics of the interaction and the formation of the compact objects. So we have set up a campaign to try to find those, and let's first look at looking for black holes. So the question is, how do you find a black hole? Because that's the kind of thing that you try to observe, right? You try to find a dark object with on dark sky. So you find them easily when they interact, right? You find them through X-ray binaries, so you find them through gravitational waves. But those are indeed the phases that we already have a lot of observation because it's easy. Don't tell that to somebody doing gravitational waves. What I want to find is these ones before the interaction. Why? Because the orbit of those objects contain information about the collapse. And if I wait that they have interacted, then the information may be washed out. So I'm just looking at Kepler laws because that's robust. And unfortunately, you cannot detect that directly, but you can try to find binaries for which the only possible or realistic explanation is that it has to have a black hole. So we do that with spectroscopy, and we're going to look at spectral lines. In a binary, the spectral lines is going to be moving due to the Doppler shift, right? And so this is a model. If I just show you observations, that will look like this. So I give you 5 seconds to tell me whether there is a second companion in this or not. We know there's a companion because it's in a binary, it's moving, but do you see the spectral signature of it? Well, by eye, it's very difficult, but there's a technique which is called spectral disentangling, which mathematically is allowing you to reconstruct and to the two spectra, the spectra of the primary stars, which is in black, and then in this object, the spectrum of a faint stars in green in it. So that would not be a black hole plus a mean sequence massive stars, because we see the light from the companion. So those are interesting stars. I can talk a little bit about it if I have time. But what we really want to see is this. Even with the best possible observations, we cannot find the signature of a hidden companion. But that companion, we can measure its mass, and it is massive. It is 10 solar mass. So the only explanation is that this is indeed a black hole. It cannot be a neutron star. 10 solar mass is much too massive for a neutron star. And so we find about a dozen objects, but those are the two best candidates. Oh, well, not candidates, but the two best systems. Just to convince you even more, if there was a normal star in it, what we should detect is the red curve, but we see the blue curve, right? So it is indeed a dark object, which is in the first case more than 7 solar mass. It is in an eccentric binary. In the second case, it is more than 10 solar mass. It is in a non-eccentric binary, and this is interesting. Why is it interesting? Because if there would have been any mass loss during the formation process of the black hole, during the core collapse, or if there would have been any kick, you would have had an eccentric orbit. So this is, to me, one of the best examples, well, I'm biased, I'm gonna say the best example, that massive stars can form and collapse directly into a black hole. And that's an important ingredient for people doing galaxy evolution and injection of angular momentum and not angular momentum, just momentum into the intergalactic medium. Let's have a look at the helium stars, and I've just seen that I've only 5 minutes left. So while we were looking for black hole, we actually found some of those helium stars. They are quite hot, quite small, so they are really dim in the optical, but we can find them just after the interaction phase, at the moment where they are still bloated. However, I'm going to skip that because there's an even better results from colleagues, so those are the one I want to skip. But those are colleagues, Maria Droth and Ylva Goedberg. Rather than using spectroscopy, they've been doing photometry. And rather than doing photometry in the optical, they've been doing photometry in the ultraviolet, because those objects, they are so hot that they have a strong ultraviolet flux. And they've been able to identify a population of hot objects that are probably helium burning, so those are helium stars. They are to the left of the zero-H mean sequence. Not only they can detect that on a color magnitude diagram, but they can measure the properties using spectroscopy, and you see that those are objects that are in the helium burning phase, 2 to 4 solar mass stars, so that's above the Chandrasekhar mass. So those are perfect candidates to be the progenitors, the long-thought progenitors of hydrogen-poor supernovae, the type 1c supernovae. All right, so this is again one of the examples, the same example of the evolutionary phases. Just want to mention that we have a bright future in the observations. There's missions, astroseismic missions, that will look at the properties of the massive stars on the mean sequence, but I would also like to suggest that we try to see whether we can detect some of the helium stars and some of the rapidly rotating stars after the interaction with those missions. There's a new satellite, which is called UVEX, that will be great to observe strip stars at different moments in the evolution. Also great to observe supernovae in the ultraviolet, because that has never been done. And the reason is that any ultraviolet facilities that we have, like Hubble, are not able to repoint in less than 48 hours. We will be able to be on target in 3 hours after the supernova detection. Oops, one more. Gaia, DR4, should produce orbits of 200 OB plus black hole systems. So that's something that in a year and a half from now, we should have the statistics, how many stars collapse directly into black hole, how many of them have ejected masses. If we don't see any, that will tell us that a lot of those are disrupted and that many of the binaries don't survive the first collapse. And then, of course, a combination of facilities like Black Gem, the Einstein telescope, or other gravitational wave interferometers. And UVEX will teach us a lot about gravitational wave mergers and their electromagnetic counterparts. So in the next 2 minutes, I've been talking about single stars, I've been talking about binaries, but I actually have a confession to make. Most of them are triples or even quadruples. And this is an example. That is a magnetic massive star with a beautiful nebula. We found that even if it's magnetic massive stars, it's actually in a long period binaries with a period of 26 years. And that the age of the two stars are not identical. They have an age that differs by more than 25%. And that is, of course, impossible because they're formed together. They cannot have been formed by capture. So our explanation is this one. So now I start the movie. It started with 3 stars. And the 2 stars got closer or merge, creating the beautiful nebula, while at the same time, this merging process has created a strong magnetic field, and that was predicted by theory. So by having not 1 star, not 2 stars, but 3 stars, you can at the same time explain self-consistently all the properties of this object, but also solving an important question about one of the mysterious properties of single stars, that was that why only 10% of them have a magnetic field. That's because the merger rate of massive stars or massive binaries is about 10%. Well, that could be one explanation. It's only one object. There may be other ways to produce magnetic field, but this one was, I think, quite convincing. That's my conclusion. I think that we need, as a community, we've been opposing single stars and binary evolution for too long now. I think we need to gain a change of paradigm. Multiplicity is a time-dependent property, so you can have a single star that will become binary by capture. You can have a binary that will become a single star. And as I mentioned, a lot of them actually start in triple or quadruple systems. But what we do have is a succession of phases, and those phases are dominated by single star processes, binary interaction processes, but also dynamical processes into multi-body systems. Thank you for your attention, and if there are any questions, I'm here to answer them.